The night sky, especially far from the hustle and bustle of cities, is filled with thousands of stars, creating the impression of infinite cosmic space. Yet this is only a tiny fraction of all celestial bodies in the universe. Billions of faint stars remain invisible to the naked human eye. Such an immense number of stars inevitably raises a question: do planets orbit them? And if so, are any of them Earth-like? For millennia, this question captivated human imagination. And now we finally have an answer. Yes, planets do exist and orbit other stars. Our Sun is surrounded by a whole family of planets, each unique in size, composition, temperature, and surface features. This remarkable diversity suggests that planet formation is not a rare phenomenon. Even if it were, given the sheer abundance of stars, it would be surprising if planets existed only around our Sun. For a long time, this question troubled astronomers, who faced enormous challenges in detecting such planets. Planets are faint and distant, hidden in the glare of their host stars, making direct observation nearly impossible. Therefore, scientists had to rely on indirect detection methods. Imagine two children, one small, one large, holding hands and spinning around. The smaller child traces a wide circle, while the larger one moves in a much tighter orbit. The same principle applies to a star and its planet. While the planet orbits in a large path, its gravitational pull causes the star to wobble slightly in a much smaller orbit. For years, astronomers searched for this subtle motion in nearby stars, but it was so minuscule that it remained undetectable, and no true planets were found. Everything changed dramatically in 1992, thanks to Alexander Wolszczan and Dale Frail. They discovered two planets orbiting a pulsar, the remnant of an exploded star. It was widely assumed that a supernova explosion would have destabilized any planetary orbits, so finding planets there was completely unexpected. Nevertheless, their existence was confirmed, and a third planet was later identified. These were the first known exoplanets, planets outside our solar system. While groundbreaking, this discovery alone wasn't sufficient to draw general conclusions. Pulsars are highly unusual objects, and the planets likely formed from leftover debris after the supernova, a process vastly different from how our solar system formed. Thus, the question remained open. Do planets orbit ordinary, sun-like stars? The answer came soon after, in 1995, when French astronomers Michel Mayor and Didier Queloz announced a major discovery. They found a planet orbiting 51 Pegasi, a sun-like star located 50 light-years away. They used the same spinning children principle. The star exhibits tiny rhythmic motions caused by the planet's gravitational pull. Although these movements are too small to see directly, their effect can be measured through the Doppler effect. When the star moves slightly toward Earth, its light shifts toward the blue end of the spectrum. When it moves away, the light shifts toward red. Detecting these minute shifts requires extremely precise instruments. Mayer and Queloz successfully applied this radial velocity method to confirm the planet's existence. The planet, named 51 Pegasi b, had some surprising characteristics. Its orbital period is just 4.23 days, meaning it orbits extremely close to its star, no more than 8 million kilometers away. By comparison, Mercury is about 55 million kilometers from the Sun. Moreover, the magnitude of the Doppler shift reveals the planet's mass. The larger the planet and the stronger its gravitational influence, the greater the star's motion. The problem was that 51 Pegasi b turned out to be at least half the mass of Jupiter, or even larger, which, according to prevailing theories of planet formation, seemed impossible so close to a star. Such a massive planet couldn't have formed in that hot inner region. However, the planet didn't violate formation laws. It simply didn't form there. Instead, it likely originated farther out, similar to Jupiter, and then migrated inward due to interactions with the protoplanetary disk surrounding the young star. In our solar system, Jupiter's inward migration was halted by gravitational interactions with Saturn, fixing it in its current orbit. But 51 Pegasi b encountered no such obstacle and continued moving inward until the surrounding material was depleted, leaving it in a tight, hot orbit. Planets like this became known as hot Jupiters. Following this discovery, other astronomers began actively searching for short-period planets and soon found several more hot Jupiters. Initially, skepticism surrounded these findings, as other phenomena, such as pulsating stars or background stellar interference, could mimic planetary signals. Scientists openly acknowledged these possibilities, unwilling to deceive themselves. True science demands critical scrutiny. Researchers welcome the chance to test and potentially disprove their own ideas. Everything changed in 1999 with the discovery of HD 209458b, a planet with a 3.5-day orbit whose orbital plane is aligned with Earth. This means it passes directly in front of its star during each orbit, a phenomenon called a transit, causing a slight periodic dimming of the star's light. This provided direct visual confirmation of an exoplanet, and the scientific community quickly embraced the discovery. The amount of starlight blocked during a transit reveals the planet's size. Larger planets cause greater dimming. Combined with mass estimates from Doppler measurements, scientists can calculate the planet's density. Gas giants, like Jupiter, have low density, while rocky planets, like Earth, are much denser. Remarkably, these physical properties can be determined without ever directly imaging the planet. In 2009, NASA launched the Kepler Space Telescope, designed to monitor the brightness of 150,000 stars in search of such transits. The mission was a resounding success. By 2015, Kepler had confirmed over 1,000 exoplanets, with another 500 verified from ground-based observations, bringing the total to 1,500. Thousands more candidates awaited confirmation, vastly expanding our understanding of alien worlds. All these planets were found using indirect methods. While direct imaging remains extremely difficult due to the planet's faintness, it's not impossible. In 2004, the first direct image was captured of 2M1207b, a planet 5 times more massive than Jupiter, orbiting a low-mass brown dwarf, a type of failed star, discussed later. This planet is relatively easy to observe because it's young and still hot from its formation, glowing brightly in infrared light. One of the most stunning directly imaged exoplanets orbits the star Beta Pictoris, With a mass 7 times that of Jupiter and a 20-year orbit, its changing position across multiple images over the years beautifully confirms its motion around the star. We've directly imaged only a handful of exoplanets because the process is technically demanding. But as technology advances, we'll capture more images and learn far more about these distant worlds. Exoplanets display astonishing diversity, but hot Jupiters were the first to be found due to their large size and rapid orbits. With improved instruments, we've now detected much smaller planets, some even smaller than Mercury, and only slightly larger than Earth's moon. Planets between Earth and Neptune in size are called super-Earths. To date, over 500 planetary systems have been identified, some hosting up to 7 planets. Exoplanets orbit all types of stars: sun-like stars, red dwarfs, massive blue stars, and even aging red giants nearing the end of their lives. There's even a very ancient planetary system where the host star is 11 billion years old, meaning its planets were already 6 billion years old when our solar system formed. Some planets orbit binary stars, proving that such configurations, once thought implausible, are not only possible, but real. This vast population of planets leads to a remarkable conclusion. Our galaxy alone likely contains hundreds of billions of planets, possibly even outnumbering stars. Given this diversity in size, Earth-sized planets must be common. We've already discovered hundreds of them, suggesting that forming Earth-sized worlds is a routine outcome of star formation. However, Earth-sized does not mean Earth-like or habitable. We don't yet know if these planets have suitable surface conditions, liquid water, protective magnetic fields, or stable atmospheres. Their climates, compositions, and potential for life remain unknown. Still, given their enormous numbers, it's plausible that a true Earth twin exists not far from us, and that our planet is just one among countless similar worlds. Astronomy has now reached a profound conclusion. The sky is filled with planets. Today, we know how to detect planets around other stars, primarily through transits, when a planet dims its star's light, or Doppler shifts from the star's subtle wobble. Exoplanets orbit every kind of star, and Earth-sized worlds are abundant, strongly suggesting that our galaxy teems with potentially Earth-like planets.